Hi class. Try raising the camera a bit to give you a better perspective and angle. Maybe it'll be easier to see the board if you're a little closer to it. All right, good. So we're going to continue the notes on gas laws. Can't remember if I talked about partial pressures last time. Well, it doesn't hurt to repeat it, right? Okay, so I'm picking up from page 414 of the text. And it talks about the question is, give it some thought. Is water vapor more or less dense than nitrogen under the same conditions of temperature and pressure? It is the give it some thought question. I call it their GIST for short. Nice play on word. It is less dense. Water vapor is less dense than nitrogen because nitrogen has a molar mass of 28.01, whereas water vapor has a molar mass of 18.01. So because Avogadro's law states that 1 mole of any gas at the same temperature and pressure contains the equal number of molecules, and they occupy the same volume, which is 22.41 liters at STP, standard temperature and pressure, then the gas that has a lower molar mass will have lower density as well, because it will occupy the same volume but has a lower mass. We did the problem on page 414. I remember I gave you homework for page 411. So let's go to that one. Practice example on page 411. It asks, the gas pressure in an aerosol can is 1.5 atmospheres at 25 degrees Celsius. Assuming that the gas inside obeys the ideal gas equation, what would the pressure be if the can were heated to 450 Celsius? So we can use the ideal combined gas law for that. P1V1 over N1T1 is equal to P2V2 over N2T2. But what things don't change in this problem? Well, the volume stays the same because it's inside of an aerosol can, so the volume inside the can doesn't change. And the amount of gas doesn't change either. So basically the equation reduces down to P1T1 is equal to P2 over T2. And then what do we have? We're told that initially the pressure is 1.5 atmospheres, that the temperature is 25, so we're going to add 273.15 to that to convert it to the absolute temperature. Pressure 2 is what we're looking for, and the temperature after we've heated the can is 450. Obviously don't try this at home because you'll have an aerosol can exploding in your face if you do that. Solving for P2, we get 3.638 185 atmospheres, and we're only allowed 2 sig figs, so we're going to say 3.6 atmospheres. Look at Mama causing trouble. Mama, what do you want? Good boy. So the next thing we want to cover is partial pressures. So the idea of partial pressures is addressed on page 417. basically the total pressure of a mixture of gases equals the sum of the pressures that each gas were exert if it were present alone. Uh, this concept was fully exploited by NASA when they sent astronauts to the moon. Uh, they initially determined, I guess through their roundtable discussions, that the best and most efficient way to build the lunar landing module was to have the lowest possible pressure of air for the astronauts to breathe. And one of the ways to achieve that is to make them breathe pure oxygen. But if you breathe pure oxygen, you don't need to breathe at a pressure of 15 pounds per square inch, because we breathe oxygen at 21% in a mixture of nitrogen and oxygen. The atmosphere is composed of 78% nitrogen and 21% oxygen. So out of the 15 pounds per square inch of air that we breathe, only 3 pounds per square inch of pressure is actually oxygen. So if you were to take away all the other gases, hi Internet, if you were to take away all the other gases, you would still have enough oxygen. You would just be breathing the same amount of oxygen, but at a lower pressure. Now, obviously, you don't want to go from 15 pounds per square inch to 3 pounds per square inch instantly. Hi, Bisola. But if you were to gradually acclimate yourselves to a pressure of 3 pounds per square inch, you would, as long as you were breathing pure oxygen, you wouldn't notice any difference. You'd be fine. And that's what they did with the astronauts. The way they came to that decision was kind of tragic, because in the first Apollo mission, Apollo 1, 3 astronauts died on the spaceship. They were bolted into the module, and a harness caught fire, and they all burned alive, because what they were doing is they were running experiments on the module, and it wasn't really possible, I guess, to get a pressure of 3 pounds per square inch, because they're on the surface of the Earth. The natural pressure on the surface of the Earth is 15 pounds per square inch. So if you wanted to fill the space capsule with air, with pure oxygen, it had to be at 15 pounds per square inch without causing extra technical difficulties. So they took the chance of running the experiment with pure oxygen inside the module, and then on top of that, they had bolted the astronauts inside. Actually, in retrospect, when you look at all the circumstances leading up to the accident, it was so foolish how they did it. And in the 60s, people were not as safety conscious as they are now. I mean, if you were to try to do something like that now, somebody would raise the alarm. But I guess back then there was a bit more cavalier attitude towards safety. But if the experiment was repeated today, accusations of murder would have been made, because that's how stupid it was to put those astronauts in a module packed full of instrumentation, with electrical harnesses, as thick as your wrist, maybe, all taped together. And if one of the wires were to short out, and that's exactly what happened, one of the wires shorted, and because of the 100% oxygen atmosphere, everything went up in flames. The astronauts were apparently dead within a couple minutes. Their vital signs were no longer detectable. So the fire was ferocious, and there was no way of opening the module within any short period of time, because they were actually bolted in. So a number of technical errors were committed, which should have been, given the intelligence of the people working on it. Wow, that's all I can say. Anyway, later on, they came to the decision that 3 pounds per square inch pressure was sufficient, as long as you're breathing pure oxygen. You get the same amount of oxygen, you get the same number of moles of oxygen every time you draw breath as you would if you were breathing air, but with only a 21% oxygen content. And there were a bunch of additional advantages to breathing pure oxygen. It meant that you only had to bring pure oxygen up into the space module to give them oxygen for the 3-day trip all the way to the moon, and they would spend another 2-3 days on the moon and another 3-day trip to get back to Earth. So they had to have oxygen brought with them, hi Marvin, so that it could cover all their needs for the whole period of time. So everything had to be factored in carefully and calculated. And remember, every pound of weight that you add to something that has to blast off into space and make it all the way to the moon has to calculate fuel needs for the rocket, and you can see that the Apollo mission had an enormous rocket to launch this lunar lander up into space. Anyhow, knowledge of partial pressures of gases is helpful in calculating these kinds of parameters for planning a mission. And that's just one of the things. Imagine all the other things they had to think about. So, what can we come to the conclusion? The gist of all this is that the partial pressure of the gas is directly related to its mole fraction. And the idea is based on Avogadro's law. The type of gas does not matter. Equal volumes at equal temperatures contain equal numbers of molecules. This idea is also exploited by scuba divers. If you want to go scuba diving, you have to know that if you're going to breathe regular air, it's only okay to breathe regular air to a depth of about 140 feet. If you go deeper than about 140 feet underwater and you're breathing 78% nitrogen, the nitrogen actually makes you drunk. It actually anesthetizes you. So when people go diving deeper than 140 feet depth, they to avoid what's called nitrogen narcosis, that the nitrogen actually makes you drunk when you breathe it in, they cut out the nitrogen, then they replace it with helium. On top of that, because you're breathing air that's so pressurized, because to fill your lungs at a depth of 140 feet, the pressure has to be about 5 atmospheres. So basically, it's there's a special regulator that senses the pressure of the water, and it releases more pressure from the tank you're carrying on your back to help fill your lungs. Otherwise, you wouldn't be able to breathe in as soon as the pressure increased. You know that every 10-year-old kid probably has this idea go through his head at least once, the idea of taking a garden hose and going to the bottom of the pool and then trying to breathe in when you're at the bottom of the pool. You can't do it. Even just 5 feet of water would prevent you from breathing in, because the weight of the water would be such that it would be stronger than your breathing muscles to expand your lungs. If you have even just 2 pounds per square inch of pressure on your chest, which is not hard to achieve, it's only a depth of maybe 1/18 of 32 feet gives you a full atmosphere, which is 15 pounds per square inch. So 1/5 of that is about 9 feet. No, 1/5 of that would be about 6 feet. So if you're under 6 feet of water, you're already getting 3 pounds per square inch. And if your chest has a 100 square inch area on it, 3 pounds per square inch equals 300 pounds of pressure. So imagine a large man standing on your chest. That's how hard it would be to breathe under 3 pounds per square inch, or about 6 feet of water. So to breathe underwater, you have to have pressurized air pumped into your lungs. And as you go deeper and deeper, because the air is pressurized, there's a higher number of moles of oxygen that can be absorbed per breath. So in fact, as you go deeper and deeper underwater, you can afford to breathe in a smaller and smaller percentage of oxygen. If I remember correctly, the deep sea diving record for people using scuba diving gear is something like 1,000 feet. But at 1,000-foot depth, the pressure is about 30 atmospheres. So you don't have to breathe 21% oxygen. You could probably get away with breathing 1% oxygen, but because of the air pressure being so high, you're still breathing the same amount of oxygen with each breath. And of course, you can't breathe nitrogen at those kinds of pressures, because it would intoxicate you. So they breathe a mixture of helium and oxygen under those extreme pressure conditions. And then they have to be very careful when they come back up. They have to decompress gradually, because if you go shooting up to the surface from that depth after breathing highly compressed air, you're going to get air bubbles forming in your bloodstream, which would kill you. That's called the bends, right? Before they knew about the existence of the bends, a lot of people died building bridges, believe it or not. The Brooklyn Bridge apparently killed several men precisely because they didn't fully understand the medical implications of the bends. They would work underwater in a caisson, which is basically a big box turned upside down and sunk to the bottom of the river, and then they would pump it full of pressurized air to push the water out. And then the workmen would work at the bottom of that, digging the mud and the sediments at the bottom of the river so they could make proper supports for the bridge. Well, if you come out of that environment after 8 hours of work, breathing pressurized air, the sudden decompression can cause the bends, and a lot of people were hurt by it, including the engineer who designed the bridge. very interesting story. Anyhow, let's get back on the topic of partial pressures. You see how science is everywhere. You can apply it to just about everything in life. So on page 418, they give you an example of how to work out a calculation using the law of partial pressure. So the question asks, what is the total pressure exerted by a mixture of 2 grams of hydrogen and 8 grams of nitrogen at 273 Kelvin in a 10-liter vessel? So let's set that up. Remember that the pressure of a gas is directly related by how many moles of the gas are present. It's based on the number of moles. So there's 2 grams of hydrogen at 2 times 1.00794 grams per mole, which is equal to 0.9921 22547. Oh my goodness, Mama, you're a pest. Go. Go in. Come on. And then you got 8 grams of nitrogen over 2 times 14.0067 for the molar mass of nitrogen equals 0.285 577 616 moles of nitrogen. So the total number of moles is these two numbers added together. So N total is equal to the number of moles of hydrogen plus the number of moles of nitrogen, which equals 0.992, etc., plus 0.285, etc., which equals 1.2777. 0016 moles of, well, let's just call it gas. Now the pressure is going to be PV equals nRT. Solving for P, therefore P is equal to nRT over V. Plugging in the numbers, 1.277, etc., moles of gas times 0.082057 liter atmospheres per Kelvin mole. And the temperature is 273 Kelvin, running out of room here, and a volume of 10 liters. When you calculate all that, and once you account for significant figures, you get a total pressure of 2.86 atmospheres. In practice example on page 419, it says that from the data gathered by Voyager 1, scientists have estimated the composition of the atmosphere of Titan, Saturn's largest moon. Again, this is going to be a place where possibly explorers will be able to land one day in the not so distant future. In fact, we could probably do it now. It'd just be very expensive and risky. Titan is Saturn's largest moon. We can't land on any of the gas giants like Jupiter, Saturn, Uranus, or Neptune because they don't have a surface. They're just big balls of gas. But the moons are small, and if they're not rocky, they're at least made of things like nitrogen ice and water ice and methane ice and all the other interesting compounds that were present in the primordial solar system. So they would be, the moons would be places where you could conduct some really interesting research. So from a scientific standpoint, they contain a treasure trove of possible scientific information, not to mention potentially also of commercial value.
The total pressure on the surface of Titan is 1,220 torr. The atmosphere consists of 82 mole percent nitrogen, 12 mole percent argon, and 6 mole percent methane. Calculate the partial pressure of each of these gases in Titan's atmosphere. Okay.
This is from page 419 of your text. So the total pressure of any mixture of gases is pressure of whatever number of gases are involved. And, you know, as many gases as there are, you have to add up all their partial pressures. Another way of stating this is that pressure total is equal to mole fraction represented by X times pressure total. Sorry, pressure of any one gas, let's call it pressure of gas number one, is equal to the mole fraction of that particular gas times the total pressure. All right, so if there was 20% of this gas and 30% of this gas and 50% of that gas, and the total pressure was 100 atmospheres, what they're saying is that 20 atmospheres of the pressure would come from this gas. Okay, so the mole fraction also predicts the pressure contribution of the gas. It's actually quite simple. So they're saying that the mixture is 82% nitrogen, 12% argon, and 6% methane. So obviously you can't breathe that. If you were to appear on the surface of Titan, you would draw about 2 breaths and then go unconscious because there's no oxygen there. But interestingly, you probably wouldn't smell anything out of the ordinary. Because methane is natural gas, it has no odor of its own, as far as I know. Argon has no odor, and we already breathe 78% nitrogen. So if you breathe in 82% nitrogen, you won't notice the difference. It wouldn't smell any different, it just wouldn't contain any oxygen. So pressure N2, the total pressure is 1,220 torr, and the mole fraction is 0.82. So the pressure exerted by the nitrogen on Titan is 1,000.4 torr. And you're only allowed, what, 2 sig figs, so you have to say 1.0 times 10 to the 3 torr as your final answer for that one. The pressure of argon is going to be, again, 1,220 torr times a 0.12 mole fraction. After sig figs, you get 1.5 times 10 to the 2 torr. And then the partial pressure of methane is 1,220 torr times its mole fraction, which is 6% or 0.06, and that works out to 73.2 torr. Oh, but I should only be writing it to 2 sig figs, so I have to say 73 torr. One of the other thing they throw in there, and they introduce it in the section on partial pressures because it's very apropos, it's fitting, is that water vapor also exerts a pressure of its own. And when you do any calculations involving gases, say on the surface of the Earth, if you want to really be accurate, you would subtract the effect of the vapor pressure because it's a small amount, but it's on the order of about 25 torr. So if you want to have an accurate calculation, you subtract that contribution of the water vapor pressure just from at room temperature, because it is significant. And of course, as ambient temperature gets higher, the vapor pressure of water also climbs. The next idea I want to bring to your attention is called the kinetic molecular theory. The kinetic molecular theory was basically a 19th century attempt to explain how gases exert pressure. And
it made a few assumptions. Basically, they said that all the gas molecules basically share the kinetic energy that's contained in the gas. If you were to take, say, a cubic foot of gas, it's composed of a bunch of air molecules bouncing around in there, and that cubic foot of gas has a certain amount of energy associated with it. And if you lower the temperature, that gas has less and less energy. The more you lower the temperature, the less energy it has. If you lower the temperature down to 273 below 0 Celsius, you reach a point where the gas has no more energy. What you reached is absolute zero. So in the kinetic molecular theory, what they did is they said, okay, let's pretend all these little air molecules are just like super balls. You know, those things you can buy at the dollar store that you throw them and they bounce back up really hard. So they treated the gas molecules like a bunch of super balls bouncing around off each other. They assumed that they had perfectly elastic collisions, meaning no energy was lost in a collision. Unlike a ball, when you drop a ball, it bounces to about 98% of the height that you dropped it from, and then the next time it bounces another 98% of the height that it bounced to on the second bounce, and so on, and it bounces lower and lower until it stops bouncing. Why is that happening? It's because the ball is transferring some of its energy to the ground by heating up the ground and by deforming the rubber of the ball, and it's not a 100% efficient process. Energy is dissipated throughout the environment. Eventually the ball loses all of its kinetic energy. Well, gas molecules don't do that. They have perfectly elastic collisions, according to the kinetic molecular theory. They also made the assumption that the molecules had no volume and that they had no attractive forces between themselves, so that all their kinetic energy was devoted basically to simply bouncing the molecules around. So kinetic molecular theory says four things. Gases are in continuous movement. 2, gas volume is negligible compared to volume occupied, which is a pretty good assumption. Gas molecules are really small, but they do bounce around and they occupy a huge amount of volume. The actual volume of the gas molecules represents less than 0.1% of the volume that the gas occupies in space because of its movement. 3, the attractive and repulsive forces between gas molecules are negligible, meaning you can ignore them. And 4, collisions are perfectly elastic. And 5, the average energy is based only on temperature. So when you make all those assumptions, you can do an equipartition of energy calculation where they assume that each air molecule has exactly the same energy as all the other air molecules. As it turns out, that's not really true because the collisions of air molecules are actually a random process, and when things happen randomly, they don't give you exactly predictable results. Sometimes you'll get an air molecule that has a little extra energy, and other times you get a molecule that has a little less energy. So what you really get is more like a bell curve distribution of energies in air molecules. Some air molecules are moving a little faster, some molecules are moving a little slower. So they developed a term called the root mean square speed. And the speed of a molecule possessing the average kinetic energy is what it represents. So we know that kinetic energy
is equal to 1/2 mv squared. Well, actually they use mu for air molecules. So E is equal to the average kinetic energy of the gas molecules and mu is the root mean square, RMS. Actually, that's how they calculate it. And it's the speed of a molecule possessing average kinetic energy. Because like we said before, they don't all go exactly the same speed. Some go a little faster, some go a little slower. Now, here's something that is kind of cool, but also kind of hard to understand at first. On page 422, they talk about it. It says, consider 3 samples of gas, HCl at 298, H2 at 298, and O2 at 350 Kelvin. Compare the average kinetic energies of the molecules in the 3 samples. So, the most important consideration that describes the energy of a sample of gas is the temperature. You can have 2 completely different gases, but as long as they're at the same temperature, they have the same kinetic energy. But here's the thing. The lighter gas is going to move more quickly if you look at each individual molecule than the heavier gas, even though they have the same kinetic energy. Let me give it to you in terms of ballistics. If you want to have a bullet that has the same kinetic energy as another bullet, the 2 bullets have to be moving at the same velocity, provided they're the same weight. If the bullets are different weights, then the lighter bullet has to move faster to have the same kinetic energy. And the same idea applies to gases. So 2 gases that are at 25 degrees Celsius, they have identical kinetic energy. But if you were to look microscopically, you would see that the gas that has the lower molecular weight is actually moving faster. The individual molecules are moving faster, but they have the same kinetic energy as the heavier gas, as long as the temperatures are the same. So with that in mind, we're going to answer the give it some thought question. So HCl and H2 will have the same average kinetic energy. Because they are both at 298 K. O2 will have a higher average kinetic energy due to its higher temperature. Of 350 K. Now, if you were to talk about the actual velocity of individual gas molecules, because hydrogen is much lighter than hydrogen chloride, then the individual molecules of H2 will be moving faster. But these 2 have identical kinetic energies at 298 Kelvin. It's just that the hydrogen atoms have to move, hydrogen molecules have to move faster to have that same kinetic energy. They once explored, there was a guy on the internet who explored the notion of using helium, compressed helium, to drive pellets in his pellet gun, because he reasoned, according to this idea of the kinetic molecular theory, that if you used the gas that was made of smaller, lighter molecules, the smaller, lighter molecules would be able to follow the pellet down the barrel more effectively because they have higher velocities due to the lower mass. So they would be able to more effectively transmit momentum to the accelerating pellet as it was leaving the barrel of the gun. He did a test, and sure enough, he achieved higher velocities with pellets on his air rifle when he used helium gas as the propelling medium. I'm going to stop there because we're already up to 35 minutes. And I'm going to
ask you to do, you don't have the textbook. I can't ask you that. You know what I'd like you to do instead? Okay, I'll do this. I'm going to assign a mock test. We haven't covered the whole chapter yet, but I can give you the first three. I'll give you the 4 questions of the mock test, and I'll show them to you, and I'll maybe I'll post them as well. Yeah, you know what I'll do? I won't show them to you because this back camera isn't going to have enough resolution. In the video that follows this one is going to contain the questions for the mock test. So do your best, and then tomorrow I'll give you the solutions to the mock test, and then I'll finish up the last bit of notes for this chapter, which is only about 5 or 6 more pages. Okay, so I'll see you tomorrow, or rather, I'll see you on Monday. Also remember that I'm turning in your report card marks for Monday. If you have some outrageously outstanding thing that you want to hand in, let me know. You can always email me. Let your classmates know. There's a couple kids who still aren't really fully online. I don't know what to say to you other than, take charge of your own education. You're not babies anymore. But talk to me. You can put a message on YouTube. You can reach me on Instagram, or you can reach me on the school email. Either way, I'll get to it. I'll get to you sooner or later if you communicate to me. Okay. All right. So I'll see you on Monday. Bye-bye.